EMI filtering, EMI filters or EMC filters, what it is, how it works, and what kind of components we can see in this kind of equipment. EMI filters helps to meet requirements, especially for conducted emission, but also for radiated emission. We can protect power supply cables and also our transmission line cables. We also filtering some components on our PCB. We are using decoupling capacitors. So those aspects, it's quite broad. We've got different, but today I will show you simple information about filtering, especially on power supply inputs or outputs is very similar, and I will show you some examples of filters. Here is one of filter. I will show you in a second what kind of components we've got here. I will show how it works. We've got different filter from other device. Also, we've got some development kit for design filter for huge currents, because of course we need to make sure that our components work properly for those voltage and current, so we can have very big EMI filter, smaller, very small, and even much smaller. But what kind of components we've got here? Here is filter for mains for power supply. Here is input, here is output. Usually in mains, in power supply, we've got 2 or 3 lines. We've got neutral line and protection earth. What we can see here on the input on the filter, we've got fuse on the beginning. It's very important to make sure that you've got fuse if you use next components. So we've got fuse, then we've got varistor, or we can use TVS diodes, but here we've got varistor. Then we've got capacitor between lines, maybe, okay. Capacitor between 2 lines with resistor. Why this resistor is important? For safety, to discharge those X capacitors. Then we've got common mode choke. So we've got common mode choke, and also we can have additional capacitor between lines, but also we've got capacitors to protection earth. Maybe I can place it here. We call it CY capacitor. So looks simple because it is simple. Of course, we've got different component characteristics and details are very important. But for now, we've got schematic of our filter. So from input, output. But why we've got different components and connected in such a strange way? Because we've got two modes of disturbances: common mode noise and differential mode noise. Differential mode and common mode. What does it mean? That in differential mode we've got transmission one way to the load and going back other line. So we've got symmetrical disturbance. Different name for differential mode is symmetric disturbance. But common mode is asymmetric. So we've got one line to load, second line, and other. It could be ground reference plane, protection earth, or enclosure, but it's different path, and our disturbances goes here, here, and here, coming back, because we've got source, noise source connected to those aspects. This is like here. Here is our differential mode. That's why we've got different components. Which component work for which is differential or common mode? So, X capacitors we've got between two lines. So, it is our differential mode filtering, because we place capacitor here, so our current loop is smaller. We make short for higher frequency here in our differential mode. If I would place the same capacitor X between those two lines, it's change nothing, because two lines are shorted. Then we've got common mode choke. The name tells us that we've got common mode disturbances. So this common mode we place here. And also Y capacitors to make smaller loop for high frequency current. So we place those capacitors between each line to the earth and here. So we make smaller current loop here, so we protect our load. So this is very simple explanation of how filters works, but we need to remember that all components in high frequencies has different characteristics. So we've got two main components for solving EMI or EMC problems. First component, it's similar to this common mode choke, it's inductive component, and also we've got capacitor. So two main components, we've got induction and capacitance. Now when we will look at frequency characteristics according to impedance or insertion loss of those components, we can see this kind of charts. Here is frequency, here we've got attenuation, insertion loss, or Z impedance. For capacitor, we've got similar frequency, insertion loss, or impedance. So, how those components works? Maybe you remember from your education that we've got impedance. What is impedance? Impedance Z. Impedance it tells us what the current how current easy can go through this path, because current is looking for low impedance path. Of course, we've got also in impedance resistance, but for high frequency currents we've got additional components. So we've got J omega L, so we've got inductance here, plus 1 by J omega C. So we've got capacitance. In omega we've got frequency 2p frequency, so we've got frequency here in this place and this place. When we will look on those parts of our equation, we can see that ideal inductance, our ideal component, has, if the frequency goes higher, this component is bigger, so our impedance is higher. So we've got something like that. If we've got higher frequency, the higher impedance of this component. This part with capacitance, we've got opposite side, because 1 by those capacitance, so we've got different aspects. If higher frequency, so this component is smaller, so our impedance goes down. So capacitor has something like that impedance. In higher frequency, it short our currents, high frequency currents, and its ideal component. But we live in real world, it's not ideal, unfortunately. So in real components we've got additional phenomena, because between those wires in inductive component we've got capacitors. So we can tell that we've got some parasitic capacitance in our inductive component, so it makes similar like that. So our real component has this kind of characteristics, so it suppresses our current, high frequency current. In this area, this point is self-resonant frequency point. Also in capacitor we've got some parasitic or additional inductance of our connection. connections especially. So we've got this kind of characteristics. So our capacitor has this kind of characteristics. So it's band pass filter. In this band it's low impedance for current. We've got also here self-resonant frequency, and remember that different components has different characteristics for different frequency, so we need to make sure that in our filter design we use components according to our disturbance. How to measure it? Usually we measure it via listen on conducted emission, but much more about test methods, measurements, I will tell you in another videos. So please subscribe, please send your colleagues this video if it's of course helpful for you. My name is Tom, I'm EMC engineer from Poland. See you next time.